Okay, in this session we're going to look at multiplexers and latches. So first off, we're going to look at the idea of inverting gates. Then we'll look at multiplexer circuits, which are just combinations of the basic circuits we've learned so far. Then we're going to look at latches, and then we're going to look at a specific type of latch called the gated D latch. First off, though, inverting gates. So each of the gates presented previously, so our NOT, AND, OR, and XOR, can be implemented with an inverting output. So as NAND, NOR, and XNOR. So the N stands for NOT, pretty straightforward. So the schematic symbol for each contains a small circle, as we've seen for the NOT. So one of the common ones that are used is the NAND gate, and we're going to look at some examples of that going forward. And this is what it looks like. So the AND gate, you remember, has the two inputs, so A and B, or I0 and I1. And remember that with the AND gate, both of the inputs must be 1 for the output to be 1. But with the NAND gate, it's actually the opposite. So any of the inputs that are not 1 and 1, so for example, 0 and 1 results in 0, but the inversion of that becomes 1. Okay, and we'll see the power of the NAND gate in some examples in a few minutes here. So the concept of multiplexers is when we start combining simple logic gates together to form more complex logic. And this is an example of a multiplexer here using a NOR gate and some NAND gates, right? An AND gate with our inverter makes it a NAND gate. So what I want to do is I want to actually step through this two-input multiplexer example by using a truth table. So here's our example here. And in this truth table, the X indicates that we don't care. Well, what do we mean we don't care? Well, let's actually go through each of the rows in our truth table. I find that the best thing to do is to get out your pencil or your drawing tool or whatever tool you have and start to just work your way through. So starting with our first row of our truth table here, we're starting with A is equal to 0, or sorry, A is equal to 1, I0 is equal to 0, and X we don't care, or I1 we don't care, so we put an X there. Well, let's start plugging in values to see what happens. So in this particular example here, we're going to plug 1 into A, and we're going to plug 0 into I0. Okay, and if we go to our first gate here, of course, I0 will be represented here as 0, and A, if we follow this path, will be a 1. Okay, now with our AND gate, a 0 and a 1 would end up being 0. It's not A and B, so in that case, the result will be 0. But with our inversion, right, with our inverter here, it's the opposite. So this value here becomes 1. Okay, now with our A here, as a value of 1, we pass it through our NOT gate, so it passes in as 1, but because it's an inverter, it passes out as 0, so it's represented here as 0. And because this is a 0, the way that the logic of a NAND gate works, we know that if both of these aren't a 1, right, then an output would be 0 initially, and inverted would be 1. So we know that this is going to be a 1. Okay, and then outputted, the inversion of this, it would be 1, so the result of that, of course, then would be 0. Okay, so that is our example of the first row of our truth table. If we go to the second row of our truth table here, I'm just going to erase this out. If we go to the second row of our truth table here, let's say that we pass in A as 1 and I0 as 1. Okay, so if we pass A through our inverter, then we know that it's going to be 0 here, which means that it doesn't matter what I1 is. We know because A is 0 that the output is going to be 1. Because anything ANDed with a 0 is going to be 0, and the output will be 1. So hopefully you're starting to see the logic of this here. Okay, so we don't care what I1 is right here, because we know that it doesn't matter if it's a 0 or a 1. The output is going to be 0, inverted is going to be 1. Okay, so that's the logic here. Same thing in this previous step, right? And then up here, we pass down our 1 and our 1, right? The output of the AND would be 1, but the inversion of that would be 0. So 0 and 1 being 0, right? The output would be 1. Okay? Then let's do one more here. Let's do the, so I'm going to erase this out. Do that here. And then looking at our third row here, if A is 0 and I1 is 0, right? Let's follow the logic through. If A is 0, it will be 0 here, which means we know without caring what I0 is that the output is going to be 0 and 1 is 0, inverted is 1. So we know the output here is going to be 1. And then if I is 0, we know that the output then would be 0 and inverted is 1. So we know here we have two 1s, which when ANDed would be a 1, but inverted will be 0. Okay, so that's how we get this value here. Okay, so hopefully you're starting to get the idea here. So that's our truth table. Let's go through the last one here where A is a 0 and I is a 1. And I1 is a 1. So A is 0. I1 is 1. And then if A inverted is 1, right, and we have I1 here is 1, the result of that will be 1, inverted will be 0, right? So then again, it doesn't matter what I0 is. We know that the result of the AND is going to be 0, and inverted is going to be 1. All right, so that's our multiplexer truth table example. Let's look now at combinational logic. So the logic gates we've just seen are referred to as combinational logic. So that example is a combination of gates, and our truth table becomes a little bit more complex to understand. When the output at any moment depends on the current state of the inputs, then that's combinational logic. So they have no memory of past inputs or outputs. Only in the moment. So whatever's coming in goes through our combination of gates, our combination of logic, and produces some sort of an output. Latches, on the other hand, can maintain state. They do not directly permit data storage. Data storage is created by using feedback from a gate output back to the input. But a latch is a single-bit memory device created in this way from logic gates. So here's an example of a latch, and it's a simple example called the set-reset latch, or SR latch. So based on the inputs S and R, over here on the left-hand side, the circuit can either set the output Q here to high, to a 1, reset Q to low, or cause output Q to be held at its last value. So in the hold state, both S and R are low, and the state of the output Q is retained. So basically we're going in a loop, maintaining Q as it was. Pulsing S high, in this example here, so S is being passed into what we can see here as an OR gate. So from going from low to high and then back to low, this causes the output Q to go high and remain at that level. So pulsing R high causes Q to go low and to stay low. So if we pulse R high here, basically it's a reset if we're thinking. So set and reset. So if both S and R are set to high, the R input overrides the S input, and sets Q to low. The next example is what we call a gated D latch. And the gated D latch has many uses. So it uses an additional input, E, that enables or inhibits the passage of data through the circuit. So the D input here passes through the Q output whenever the E enable input is high. So E is basically saying we can change the state as long as it's high. But if we turn off E, then the state will remain the same as what it was. So I just want to go through the truth table here so we can see how this logic actually works. And like I mentioned again, this is a useful exercise to do. So let me set up my drawing tool. And let's go through this first row here. So if we set D as 0 and we basically enable E, so we turn E on, then we can work through all of this logic here. Now, if we set D to 0, the output of Q will also be 0, but we're setting D to a value because E is effectively turned on. So let's go through. So if we take D as 0 here, we go through our NOT gate, then D arrives here as a 1. A 1 and a 1 is a 1. So that's an AND, but inverted becomes a 0. If D is 0 here, we know that because it's a 0, that the AND will make it a 0 and inverted it will be 1. Okay. Now, if we pass this logic here, we know that if this is a 0, that the output is going to be a 1, right? Because 0, and it doesn't matter what this particular input is, the result will be 0 and inverted will be 1. So we know then that the value passed from here up to this AND gate makes it a 1 and a 1, which makes it an AND 1. Inverted makes it a 0. Okay, so we know that if D is 0, then the output Q will be 0. Okay? Now let's do the second row here where D is equal to 1 and E is turned on. So if we set D to 1 and E is 1, then we know that 1 and 1 here will be 1, inverted will be 0. Okay, and because this is 0, we know that the output here is going to be 1. So we don't really even need to do anymore. We know that the output for Q is going to be 1, as long as E is turned on. Now, if E is turned off, what happens is that whatever the state of D was the last time is maintained, and that's why it's called the gated D latch. So when E is high, the output will be D, whether D is 0 or 1. And then when E is low, Q will just maintain its state. And this is whatever the last value of D was. So similar to what we saw with the SR latch, the gated D latch works in the same fashion. So with this in mind, it's important to make sure that you initially set D to a desired initial value. So maybe if you're setting a set of registers, for example, a set of space in memory, that's never been accessed or used before, that you set everything to 0 so that we have an initial state that we know and that we expect, so that when we access that, remember, we know what the initial values will be. All right, just to summarize, we looked at inverting gates. So the AND inversion to the NAND is the one that we saw quite a bit in our examples here. We looked at multiplexer circuits, so how to combine our basic circuits, our AND or NOT XOR gates, and our inverted circuits, inverted gates into more complex logic, for example, to create a latch that allows us to maintain a state in memory. And we looked at specifically an SR latch, and then we looked at a gated D latch. All right, thanks for tuning in, and we'll see you in the next session.